Hey everyone, and welcome to The Explainer. So, you've probably run into this, right? You have something really complex from the real world, and you try to cram it into a simple spreadsheet, and it just falls apart. Well, today, we're diving into the solution for that exact problem, object-oriented databases.
So here's how we're going to tackle this. First, we'll talk about why traditional tables sometimes just don't cut it. Then, we'll shift gears and start thinking in objects. After that, we'll pop the hood to see what's inside, do a little head-to-head comparison, weigh the pros and cons, and finally, take a look at what this all means for the future of data.
Okay, let's get right into it. First up, a challenge that pretty much anyone who's ever worked with data has faced, the good old-fashioned limits of tables.
Think about it. A car. It's not just a list of specs, is it? It's this intricate machine with parts and systems and things it can do. So how in the world do you capture all of that richness, all that interaction, in a flat two-dimensional grid? That is the fundamental problem we're going to unpack.
And right here, you can see the mismatch perfectly. On the left, you've got your standard relational table. It's clean, it's organized, and it's awesome for simple facts like make and model. But look at the right. That's reality. A car has an engine, wheels, doors, they all work together. It has behaviors like accelerating and braking. A simple table just can't represent that dynamic reality without a ton of complicated joins and workarounds.
Okay, so we've seen the problem loud and clear. Now let's explore a totally different way of thinking about data, one that actually embraces complexity instead of trying to flatten it out.
And here it is, the big idea. An object-oriented database, or OODB, doesn't think in rows and columns. Nope, it stores data as objects. And just like in object-oriented programming, these objects are like little self-contained packages. They hold both the information and the code to work with that information, all bundled up together.
This quote just nails it. The main benefit here is that it's intuitive. Because the database model actually reflects how things work in the real world, it just makes more sense. You're not trying to force a square peg into a round hole anymore. You're building a database that gets the world in the same complex way that you do.
So, we get the concept now, but how does it actually work? Let's go into the hood for a bit and check out the components that make this whole model tick. Let's start with the absolute basics, the fundamental building blocks. You can think of these four things: objects, classes, attributes, and methods, as the core vocabulary for any object-oriented system.
The object is really the star of the show here. It represents an actual, real thing. So if we go back to our car example, a specific red Tesla with a specific VIN number, that's an object. It's got its own data or attributes, like color is red, and it has things it can do, its methods, like the ability to accelerate. Right, so if that specific red Tesla is an object, then the general concept of car is the class. A class is basically the blueprint. It lays out the rules saying that all cars will have attributes like make and model and methods like brake. It's the template that lets us create thousands of unique car objects that all follow the same basic structure.
Now, beyond those basics, there are three concepts that give these systems their real magic, and I like to think of them as superpowers for your data: inheritance, encapsulation, and polymorphism. This is what makes the whole model so flexible and powerful.
Let's just take inheritance for a second. It's incredibly efficient. It means we can create a new sports car class that automatically gets all the stuff from our main car class. We don't have to rewrite the code for wheels or doors, it just inherits it. We only need to add the new special stuff, like maybe a turbo boost method. And the other superpowers, like encapsulation and polymorphism, help protect your data and make your code even more flexible. It's a really powerful combination. Okay, so these are all fantastic programming ideas, but what makes this a real, trustworthy database? Well, that comes down to a few essentials: persistence, identity, and the ability to handle transactions. These are the features that let you actually rely on it for your important data. First and foremost, persistence. This is what lets your objects actually get stored long-term. When you close the program, the object doesn't just poof, disappear. It's saved. Then there's identity, which means every single object gets a unique ID, so there's never any mix-ups. And finally, transaction support means that complex operations, like transferring money, happen completely or not at all, which keeps your data safe and consistent. Without these, you just have a cool program, not a database. All right, we've got the theory down. Now it's time for the main event, the showdown. The good old relational model versus the object model we've been exploring.
This table really lays it all out. Relational databases, they use tables. ODBs, they use objects. To link data, relational systems use special keys, primary and foreign keys. But ODBs handle relationships directly with things like inheritance. And maybe the biggest difference? With relational, you talk to it using SQL. With ODBs, you use more specialized languages, and you actually change the data by calling the methods on the objects themselves.
And hey, this isn't just some academic concept. You see these ideas out there in the real world all the time. MongoDB, a hugely popular database, stores data in flexible, object-like documents. Redis is a lightning-fast, in-memory store built specifically for complex data structures. And then you have more traditional ODBs, like Object Store, which is a big deal in specialized fields like engineering and CAD design.
So, with all of that in mind, when should you actually use one of these? It's not a silver bullet. So let's get into a really honest, balanced look at the advantages and the disadvantages.
The advantages are pretty compelling. First, they are just built for complexity, plain and simple. Second, thanks to things like inheritance, they really encourage you to reuse code, which means you can develop faster and cleaner. And a big one, they can be incredibly fast when dealing with deeply interconnected data because they don't have to do all those complicated table joins.
But, and this is a big but, there are definitely trade-offs. The learning curve can be pretty steep, especially if you're not already comfortable with object-oriented programming. You also lose the universal language of SQL, which can cause some serious headaches. And because the market is just smaller, you might have less community support, and you run the risk of getting locked into one specific vendor system.
And that brings us to our last section. Let's pull all these threads together and think about what role these databases might play in the future.
So, what's the big takeaway here? Object-oriented databases are an incredibly powerful tool, but they are a specialized tool. They absolutely shine in areas like engineering, scientific research, or multimedia, where the data itself is just really, really complex. They are not here to kill off relational databases. They're another vital tool in a developer's toolbox. Which leaves us with one last question to chew on. As our digital world gets more and more complex, more interconnected every day, is thinking in objects going to become the new default for how we handle our data? It's definitely something to think about. Thanks so much for joining us for this explainer.